Hello students, welcome back. So we had discussed about your deadlocks in the previous video. So continuing with the concepts of your deadlock. To the last we had addressed what are the methods of handling the deadlock. Now let us address each of these methods one by one. The first one we have is deadlock prevention. That is, we are preventing the deadlock from its occurrence itself and we make sure that there is no deadlock occurred. Now, how could we prevent a deadlock from occurring? We can do so by eliminating one of the necessary conditions. If you remember, in the last class we had discussed about the 4 necessary conditions on which satisfying which there could be a deadlock. So here we have a strategy for prevention. So we say that eliminating one of the conditions, there is a possibility that we prevent the deadlock. Now we will see how each of the condition could be nullified, or how is that we avoid each of the condition, and avoiding that condition, is it beneficial to the system, is there any disadvantage associated to that? We will see each one of it. Now the first condition that we have is mutual exclusion. So what does mutual exclusion tell? Mutual exclusion tells that there should be only one process at a time that is using the resources. So we talk about the resources, it should not hold some non-shareable resources. Now for example, if we talk about a printer can never be simultaneously shared by multiple processors. It is only one process at a time that can be using the printer. And if we consider a shared resource, if we talk about a file, that is only a read-only file can be shared by multiple processes. So here, what is that we are trying to convey? There are some resources in the system by nature that is non-shareable. By nature, the resource allows only one process at a time. So denying mutual exclusion, we cannot tell that we have completely prevented the deadlock. So the next condition that we have is your hold and wait. So what is the condition of your hold and wait? It says no process can be holding a resource and requesting for a new resource. So how can we avoid or how can we nullify this particular condition? Now we bring in 2 protocols to do the same. That is, the first protocol tells a particular process must request all the resources that it needs at the beginning or before it starts the process. Now, if process P1 requires 3 resources, say A, B and C, it must request all the 3 resources before it starts the execution. That is one protocol. The other protocol tells if a process is requesting for a resource only when a process does not hold any resources. Now let me continue with the same example. The first protocol tells if, let me just put it down. The first protocol tells if process P1 needs A, B, C, it must request all of it before it starts the execution. Now the second one tells if process P1 needs A, B, C again. Now if process P1 is, for example, having A and B, fine. Now process P1 wants C to complete its execution. If I have to put it in the reality terms, for example, if process needs a tape drive, disk drive and a printer. Now process 1 is already using your tape drive and the disk drive, that is your A and B. Now to complete the execution, it needs the resource C. Now process 1 cannot request resource C is what the second protocol tells. If process 1 wants to request a resource C, it has to release both A and B. It has to release both A and B, and only then it can request C. So that is what these two protocols tell. So the condition for the deadlock was if a process is holding one resource and requesting the other. So to avoid that, the protocol here is talking about it either the process has to request all the resource at the start, or if a process makes a new request, it has to release the resources it was holding, and only then it can make a new request. Now both the methods or both the protocols that is defined here is leading to low resource utilization and starvation as well. Now what is low resource utilization? Now let me just define these resources A, B, C. Now for example, I say there is a process that is using the memory, disk and the printer. Now the process is first using some part of the memory, and then it is making the permanent storage of the file into the hard disk, and then finally the process is going to print that file or document. So what is happening here? Until that the printer is not utilized at all. It has acquired the printer and the printer is kept idle doing nothing until the process is doing the other operations. So this is where there is a low utilization of the resource. Now talking about starvation, if I have another process, say P2, which is requesting for the printer, it has to wait until P1 completes all its execution and then releases the printer. Again, it is waiting for a very long time. Process P2 has to wait for a very long time, and which eventually will lead to starvation as well. So there are protocols which is there that we could avoid hold and wait, but it is also avoided, but it also comes with certain disadvantages. Now the next condition that we have, so the other condition now we have is no preemption. So what does no preemption tell? No preemption tells that a resource should not be preempted from a process. A process should voluntarily give up the resources. Now, to prevent this condition, the resources must be preempted. Only then we shall be preventing or nullifying this condition. So again, to do the same, we have a protocol. So what does the protocol tell? If a process is holding a set of resources, and if a process wants a new resource which cannot be immediately allocated, then all the resources that the process is holding shall be preempted, and the process will be insisted to restart it from again, and it has to make a new request of the process. Now if I have to just put it across, if I say there is process P1 which wants, again let me take the resource A, B, C, D, but process P1 has the resource A. Now if process P1 wants the resource B and C, and if B and C are currently not available, if it has to wait, then we preempt this also. So process P1 has no resources now. It has no resources. It has to start from the beginning. It has to again acquire A as well. So by doing this, we will be preempting the resource. But is this protocol applicable to all the resources? Probably not. Whenever we preempt a resource, the process may be in the middle of the usage. We can do that only to few resources, say memory or register, where it could save and restart. But can I do it for a printer? Now if a process is in middle of printing a document, can I preempt it? Probably not. So this protocol is there to nullify no preemption, but probably it is not applicable to all the resources. Now the last condition that we have is on your circular wait. So what does circular wait tell? If there is a process that is waiting, that is holding a resource and waiting for another resource held by the preceding process. Now let me put it this way. Now if I have process P1 is holding a resource and A and waiting for a resource B that is held by process P2. P2 is holding B and waiting for C, and P3 is holding C and again waiting for A that is held by P1. Now that is a circular wait that we have, where the last process is again waiting or requesting for the resource that is held by the first process. Now how do we break this circular wait? So having this circular wait may lead to deadlock. How do we break this circular wait? So here is a protocol to do the same. So the protocol tells whenever a process is requesting for a resource, it should request in the increasing order. Now what does it mean? Now for example, if I have a process Pi is requesting for a resource. Now it already has a resource. Let me say it is holding R2. It cannot request R1. It can only request R3. And here I have given this 2, 5, 3. These are the instances of the resource. Here I am telling 1, 2, 3 would be the order. So here I am specifying the instances of the resource. It can request for any number of resources or any instances of the resource, but it should be in the increasing order. Here we are not concerned of the instances. Here it doesn't mean that if a particular process is having one tape drive, then next it has to ask for 2 disk drive. No, it is the order here. We have to enumerate the resources in some order. Let me talk about it again later. So we have to enumerate the resources in some order. So that order, it should request only in the increasing order. Now, just requesting in the increasing order, how is it going to break the circular wait? See to the example here. Now, for example, let me put it this way. I have P1 holding R1, P2 holding R2 and P3 holding R3. Now, what is the circular wait? P1 is holding R1 and it is requesting R2. P2 is requesting R2 and P1 is requesting R2, P2 is requesting R3 and we have P3 which is requesting back R1. Now, when I say it should request only in the increasing order, so it is impossible that it could request back to the R1. That is, the last process cannot be requesting the process or the resource that is held by the first process. So this is how the circular wait could be nullified, and this is the protocol that helps us to do so. But what is the difficulty in this protocol again? The enumeration of the resources is the difficulty. Now, how do I assign the number? How do I say hard disk is number 1, tape drive is number 2, printer is number 3? How do I even do it? On what criteria can I be doing it? There are times where hard disk may be requested before the tape drive in a process or in the program. So enumerating the resource is one of the difficulty that is associated with this solution. So we have discussed the 4 solutions which says how we could be preventing the deadlock. So in all the 4 solutions, what are we doing? The necessary condition that is there by which a deadlock can occur, we are trying to prevent that condition. Eventually, we may also prevent the deadlock. So the next thing that we have is about your deadlock avoidance. So we have seen that in the methods of handling the deadlock, we had deadlock prevention and deadlock avoidance, which is actually trying to stop the system from entering into the deadlock state. So we have seen what are the methods for prevention. Now let us see what are the methods for avoidance. So how is that we could be avoiding the deadlock? We can be avoiding the deadlock by achieving or by gaining some additional information about the process and the resources that it needs. So the simplest model is every process should declare the maximum number of resources that it needs for execution. So the deadlock avoidance algorithm dynamically examines if the resource can be allocated or the allocation of the resource is leading us to deadlock. every time it is giving a resource, it shall check whether it could lead to deadlock or not. If it is leading to deadlock, probably the resource shall not be allocated. Now let us see what is the resource allocation state. Now we said that if a process wants to execute, it has to declare the maximum resources that it needs at the first itself. So what does that actually mean? So I have given a small illustration here. You can see this is the available. Now what do I mean by the available? I have 5 hard disk and 2 printers in the system. That is the number of resources that is available. It is a finite or a limited number of resources that is available. Now, process P1, to complete its execution, it needs 2 hard disks and it needs 1 printer. Now, what have I already allocated to process P1? I have allocated 1 hard disk. I have to still allocate another hard disk and a printer. So what does the avoidance algorithm do? It dynamically checks if I am allocating another hard disk to P1, is it going to cause a deadlock? If it is not causing a deadlock, it shall be granted. If it is causing a deadlock, probably process P1 shall be put to wait. Now let us see, this comes up with another concept, that is your safe state. Now let us see what is safe state. When a process requests for the resource, if the resource is immediately allocated, only if it leaves it in a safe state. Now what is a safe state? It is a deadlock free state. So if the allocation is leaving the system in a deadlock free state, only then the resource is allocated. If it leads to the deadlock state or unsafe state, probably it shall not be allocated. So this is determined by the safe sequence of the process. Now let us see what is a safe sequence. If I say this is the safe sequence, that is process P1 must execute and then process P2, and after process P2 it is process P3 and so on to Pn. If I say this is the safe state, that is process P2 should execute only after the completion of process P1. Or if there are chances, if I say there is a safe state, if process P2 executes first, probably you will understand what is a safe state when we take up a problem. What is a safe sequence? So a safe sequence, I am not numbering the process here. Please understand, it can take any number. It could be 1, 2, 3, 4, 5 or 4, 3, 2, 1. But I am telling the order of execution. So if I am executing in this order, probably that would leave the system in the safe state. So safe sequence gives the order in which a process could be executed, that leaves it in a safe state. That is, now here if there is a process Pi, it can still request for the resource that is currently available and the resource that it is held by Ij only if immediate allocation is leaving it safe. If process Pi resources needed are not immediately available, then process Pi should wait until the completion of another process that is holding the resource. Now let me put this Pi and Pj as P1 and P2. Now if P1 is requesting for a resource that is there, if allocating that resource is leaving the system in a safe state, it is immediately allocated. If it is leading to a deadlock state, then probably we request process P1 to wait until it completes until process P2 completes. So once process P2 completes, releases the resource that can be allocated to P1. So this goes on. Just to summarize about the safe state. So if the system is in safe state, there is no deadlock. If the system enters an unsafe state, there is a possibility of deadlock. And so we have illustrated the three states here: safe state, unsafe state, and deadlock state. So if a system is in unsafe state, there may be a possibility of deadlock, so the system enters the deadlock state. So what does the deadlock avoidance try here? We make sure the system does not enter the unsafe state. So what are the algorithms that we have? We make sure that it does not enter. There are two algorithms or two measures that is taken. One is for the resources with single instance, and the other one is for the resources with multiple instance. So let me address to each one of it now. So resource allocation graph algorithm. This algorithm works only if the resource instance is single instance of the resource type. Now what do I mean by the single instance of the resource type? If there is only one, that is if I have only one hard disk, one printer, one tape drive, probably I can be using the resource allocation graph algorithm to avoid the deadlock. So we had already seen the resource allocation graph previously, and a small variation to that is where it is going to avoid the deadlock. What is the variation? We have something called as the claim edge. Previously we had only two edges, that is we had the request edge and the assignment edge. Here we have another edge, that is your claim edge. Now let me talk a little about what is this claim edge. When we started discussing about your deadlock avoidance, we started with a thumb rule telling that if a process needs a resource, this resources should be claimed at the starting. That is, what is the maximum number of resource it needs for execution should be told at the beginning. Now if I say process P1 needs one hard disk and one printer. So process P1 is claiming for one hard disk and one printer. So the process P1 is not allocated with all the resources that it has claimed. Fine. Now process P1 is allocated only with the hard disk. Now process P1 starts the execution. It is using the hard disk. It is in middle of the execution. Now it requests for the printer. Now this request will be satisfied only if it leaves the system in the safe state. This request shall be denied and the process P1 has to wait if it leads to unsafe state. So that is what we say here. Claim edge shall be converted to request edge. Request edge shall be converted to assignment edge. That is, after the resource is assigned to the process, it shall be converted as the assignment edge. Now let us see the representation. as I told it to you, it is the single instance of the resource. So again, we are not depicting that tiny box inside here. So it is understood there is only one instance of the resource. So we are just using this large box. Now what does this graph tell? Process P1 is holding the resource R1 and is claiming for the resource R2. Process P2 is requesting for R1 and is also claiming for R2. Now, if we satisfy the request, if this claim edge is converted into request edge, is it leading to a cycle? Yes, if it is leading to a cycle, then probably we would not do so. Now you can see here, previously this was a claim edge, that is P2 is claiming for R2. Now if P2 is assigned with R2, it forms a cycle. So according to the resource allocation graph, if there is a cycle, there is a possibility of deadlock. No cycle indicates no deadlock. Probably if it is leading to a cycle, we may not assign it. Now here what happens? Process P1 is holding R1 and requesting R2. Process P2 is holding R2 and requesting for R1. So we make sure whenever we grant a request, we make sure that it is not leading to deadlock. So we ensure there is no cycle in the graph. So by using this resource allocation graph, we can say there is a deadlock or not, and this works only for a single instance of the resource. Now practically the resources are not of single instance. Now how do we avoid deadlock when there are multiple instances of the resource? So to do the same, we have our next algorithm, that is the banker's algorithm. The next algorithm we have is the banker's algorithm for multiple instance. I have already described it many a times. What is the resource type and what is the instance of the resource type? So the previous algorithm that we saw, resource allocation graph algorithm, that was designed only for a single instance of the resource. If there is a single instance of the resource, we can determine whether it is entering a safe state or a non-safe state using the graph. But for the multiple instances of the resource, probably resource allocation graph cannot be used. So that is when we use banker's algorithm, which is a resource allocation and deadlock avoidance algorithm. This determines whether it is in a safe state or not, whether the requested resource can be allocated or the process has to wait. So whenever a process starts, it must first priorly claim the maximum use of the resources. If the process request can be satisfied, being in a safe state, only then it is allowed, else the process is made to wait. Now why was banker's algorithm named as so? Because it was related to a banking system. So in a bank, whenever there is a loan sanction that needs to be done to a person, probably it follows the same principles. That is, there are n number of account holders in a bank and there is a total sum of money the bank holds. Let us say it a S. If a person applies for the loan, then the bank first subtracts the loan amount from the total amount that the bank has. If the remaining amount is greater than S, then only the loan is sanctioned. It is done because all the account holders comes to withdraw their money, then the bank can easily do so. Or we say the bank is trying to be in a safe state. So it allocates money only if it can satisfy the other customer needs as well. Now let us see to the data structure of the banker's algorithm. So what are the variables that is used in the algorithm? Now let us say that there are n number of processes and m number of resource type, that is P1, P2, P3 to Pn number of processes, R1, R2, R3 to Rm type of processes. Now again I stress upon the resource type and the resource instance. R1 is a type of resource which can have many more instances of that resource. Now we have 4 other variables, that is available, max, allocation and needed. Now available, let me define each of the terms, and you can see most of it is an array or a matrix. What is an array or a matrix? Why is it so? We will see it in the next slide. Now, available is, for example, in the system, there is resource R1 of 5 and process P1 is requesting 2 instances of resource R1. I said there are 5 instances of resource R1. In that, it is asking for 2 instances. Now what is my available? It is 3. So that is the available vector that I have. After allocating it to various processes, how many instances of the resource type is available? Now the next one we have is the max. What does the max mean? Now we said that for the deadlock avoidance algorithm, the algorithm have to claim priorly the maximum number of resources that it needs with its instance. Why is it a matrix? For example, I have process P1 that needs 3 resource types of instance 2, 1, 2. That is, process P1 needs 2 instances of resource 1, 1 instance of resource 2, 2 instance of resource 3. So that is the maximum requirement the process have to complete its execution. Now, what is the allocation matrix? Among the maximum required, how many resources is currently allocated to that process gives us the allocation matrix. That in the resource ABC, how many instances of that is currently allocated. Need matrix, it is obvious. It is max minus the allocation. There is a requirement a process has. There is a current allocation that is made. How many more is needed is what we will derive by max minus the allocation. Now let us just see a numerical example so that you get a better idea of the matrix and the vector that I am talking about. So this is it. Now I say the actual number of instances the system has is, there are 10 instances of resource type A and there are 5 instances of resource type B and there are 7 instances of resource type C. That is, in the system, the A, B, C is 10, 5, 7. So, I have 10 instances of resource type A. What do I mean by 10 instances of resource type in the system? A process can never request or require for 11 instances of resource type. It will become an error. My request should always be within this limit. Now, let us see what is the allocation. Now, out of this 10, 5, 7, now we can see here P0, there is 0 instance of 10, there is 1 instance of B, that is 5, there is 0 instance of 7 again. Now let me just sum this up. So it is 5, 7, 2, 5. So among the system, that is the resources in the system is 10, 5 and 7. Out of 10, 5 and 7, there are 7 instances of resource A that is allocated among the process P0 to P4. Among 5 instances of resource B, there are 2 instances that is allocated already. Among 7 instances of resource type C, there are, I'm sorry, this had to be a 5. I just miswrote it. Let me just erase it. Oh God, let me just strike it off. Okay, let me rewrite it. It is 7 to 5. So let me continue. Among 7 instances of resource type C, there are 5 instances that is allocated. Now, how many are available? Out of 10, 7 are allocated. So, resource type A, 3 is available. Out of 5, 2 is allocated. So, again, resource type B, 2 is available. Out of 7, 5 is allocated. So resource type C, 3 is available. I believe now you understood what is the available vector. Now let us see what happens in the max matrix. So what does the max matrix indicate? The process P0, to complete its execution, it needs 7 instances of resource type A, 5 instances of resource type B and 3 instances of resource type C. What is allocated? Only 1 instance of the resource type B is allocated. Now, as seen in the previous slide, I can be determining my need by subtracting max minus allocation. So that will give me my need matrix. So I can eventually do that for all the processes. So what will be given to you? It will be allocation, max and available, by which you can be calculating your need. As I showed you here, you can be calculating your available as well. So this understanding is required for me to explain your algorithms. Again, in the banker's algorithm, you have sub algorithms, that is safety algorithm and resource request algorithm, which we will see in detail one by one.